Welcome to This Explainer. Today, we're diving straight into the fascinating physics and metallurgy of electrical conductors, specifically metals. We're going to take a totally fresh look at the vital metals that literally power our modern world, and we'll be viewing them through a lens you might not have used before. It's going to be a fun ride. Let's kick things off by tackling a super common myth. You know that widespread idea out there that gold is the ultimate, absolute best electrical conductor? I mean, we see gold-plated connectors on high-end audio gear and just assume it's the peak material for moving electricity. But if that were actually true, why isn't our entire power grid wired with solid gold? I mean, aside from the obviously massive cost, right? Well, the actual rankings of metallic conductors usually surprise a lot of people. If we look at the International Annealed Copper Standard, pure silver actually takes the top spot. It sits at a whopping 105% conductivity. Then comes copper, which sets our baseline at exactly 100%. In gold, surprisingly, it trails way behind at just 70%. No way, right? It turns out gold's real superpower in electronics is just its resistance to corrosion, not its sheer ability to push power. So here's our roadmap for today. We've got 1. The magic of metal conductors. 2. Surfing the electron sea. 3. Classical versus quantum physics. 4. Why copper is king. 5. The alloy trade-off. And finally, 6. Heat, power, and final thoughts. Let's get into it. Section 1. The magic of metal conductors. Okay, so in metals, conductivity is basically all about these free-moving electrons. But here's a wild thought. You don't actually need a single specific electron to travel all the way from the power plant to your TV just to turn it on. Not at all. What's really happening is a long chain of momentum transfer between mobile charge carriers. Picture it like a microscopic, incredibly fast game of pinball happening deep inside the metal. One electron nudges its neighbor, which bumps the next one, and down the line it goes. Section 2. Surfing the electron sea. To really get a grip on how this momentum transfer works, we need to take a quick step back to the classical theories from around the turn of the 20th century. In 1900, a physicist named Paul Drude proposed what we now call the classical Drude-Lorentz model. He basically pictured a metal as this rigid framework of atoms totally soaked in a sea of electrons. Now, without an electric field, these electrons are just zipping around randomly, kind of like a gas. But flip the switch and apply an electric field? Boom. These free electrons get accelerated toward the positive ions. Governed by the drift velocity equation, they develop a resultant velocity in one specific direction. And that velocity is directly proportional to the electric field and the time they spend cruising between collisions. Section 3. Classical versus quantum physics. Now, that classical Drude model was super elegant, sure, but it had a fatal flaw. It incorrectly predicted that magnesium would conduct electricity better than copper. And, well, that simply didn't match real-world experiments. So quantum mechanics swooped in to save the day and solve the mystery. See, the classical approach assumed that literally all the free electrons in a material drift together and contribute to conduction. But the quantum mechanical approach, it revealed a totally different reality. It's actually much more like a massive multi-lane highway where only the highest energy electrons, the ones already cruising in the absolute fastest lane, actually get to do the driving and contribute to the current. When we look at the quantum approach, specifically the Fermi surface, it shows us that only specific electrons moving at a really high speed, near what's known as the Fermi velocity, actually contribute to electrical conductivity. Metals are such fantastic conductors simply because they have a ton of energy levels available right near this Fermi energy. This provides exactly the right specific electrons needed to mobilize and carry that electric charge. And you know what? This perfectly explained the whole magnesium versus copper mystery, proving once and for all that the quantum approach is definitely the way to go. Section 4. Why copper is king. This whole quantum reality perfectly explains why copper naturally dominates our modern grid, and it really all comes down to one specific magical metric: 100. In the world of quantum physics and electrical resistance, an electron's journey is basically a series of rough collisions with impurities, lattice ions, and random imperfections. The distance it manages to travel between these crashes is what we call the mean free path. Well, that number 100 represents the approximate mean free path of an electron in copper at room temperature. Think about that. It means a single electron incredibly travels about 100 atomic spacings before colliding with anything at all. That is a uniquely long, totally uninterrupted journey, which translates directly to incredibly low electrical resistance. So, when we summarize copper's winning traits, it's really a perfect storm of material science. First off, its outermost 4s energy zone is only half filled, which offers plenty of electrons ready and waiting to carry a current. Second, as we just saw, it's got that phenomenally long mean free path. And third, from a macroscopic engineering view, it has extremely high ductility. Ductility is basically a metal's ability to deform under stress without snapping. This means copper can be easily drawn out into incredibly thin wires with super tight tolerances. Thanks to this absolute powerhouse combination, copper is the undeniable optimal choice for our wiring systems.
Section 5. The alloy trade-off.
But here's the catch. While pure copper has stellar conductivity, it actually falls a bit short in tensile strength for highly demanding applications. And this brings us right back out of the quantum realm and into the macro world of mechanical engineering. To beef up a wire's strength, engineers have to mix in other elements to create a copper alloy. The problem? This introduces fresh collisions for our traveling electrons. Different elements have vastly different impacts here. Stuff like silver, cadmium, and zinc have the least effect in dragging down conductivity, but throw in elements like phosphorus, silicon, or iron. Those are potent conductivity killers. Seriously, even trace amounts of these can drastically ruin the electrical efficiency of the copper. So the principal challenge facing any alloy designer today is navigating this exact tricky trade-off. Every single time a new alloy is developed, engineers are forced to perform this really delicate balancing act. You want to push the performance curve so you can make the wire mechanically stronger so it doesn't just snap under high tension, but you have to do it without completely sacrificing its ability to conduct that precious electric current. It's tough. Section 6, Heat, Power, and Final Thoughts. We definitely can't talk about moving electricity through metals without talking about its most unavoidable and sometimes frustrating byproduct, heat. There's this concept called Matheson's rule, and it explains that a metal's net electrical resistivity is actually caused by two main things combined. First, material imperfections, like those alloy additions we literally just talked about. And second, thermal phonons. Now, thermal phonons are essentially just heat vibrations in the atomic lattice. Heat causes the atoms in the metal to vibrate wildly, right? And that creates way more obstacles for our free electrons to crash into. This is exactly why chilling copper rapidly increases its mean free path and its overall conductivity. You're essentially just calming the lattice down. Which naturally leads us to the Wiedemann-Franz law. This fundamental universal law mathematically proves that heat transport and electrical transport in a metal both rely on the exact same free conduction electrons. That's right, the very same high-speed electrons carrying your power along the Fermi surface are also directly responsible for conducting heat right through that wire. They are quite literally two sides of the exact same quantum coin. And that leaves us with a pretty massive engineering puzzle to ponder. If the very electrons that power our devices are intrinsically tied to generating their heat, how are tomorrow's materials going to evolve to keep our power-hungry world from basically melting down? I mean, are we strictly bound by the absolute limits of the electron sea? It's a fascinating question, one that continues to push the absolute limits of metallurgy and physics every single day. Thanks so much for joining me on this explainer, and remember to keep questioning the science behind the everyday objects around you.